Hey there. Ever wonder how scientists predict the future of our planet? Or how AI can help us make sense of the chaos of real-world data? Today, we're diving into two groundbreaking approaches that are reshaping how we model complex systems, from climate change to economic trends. Let's break it down. So imagine you're trying to predict how a city's economy will change if a new policy is introduced. Or maybe you're a climate scientist, forecasting temperature shifts under different emissions scenarios. These problems are incredibly complex. There are so many variables, so much uncertainty. Traditional methods often struggle because they can't adapt quickly or handle all these moving parts. But here's the twist. Researchers have developed a new framework called neural conditional transport maps that's rewriting the rules. At its core, this technique builds on something called optimal transport, a mathematical concept that's basically about moving things from one place to another as efficiently as possible. Think of it like rearranging a messy room. You want to move all the items to their ideal spots with the least effort. But when you're dealing with real-world data, like climate models with thousands of variables, it's way more complicated. Traditional methods can't keep up with the sheer scale or the changing conditions. Here's where neural networks come in. These AI systems learn patterns from data, but even they hit a wall when it comes to conditional optimal transport. That's where this new framework shines. It uses a special type of neural network called a hypernetwork. Think of it as a network of networks. Instead of following a fixed set of rules, it dynamically creates tailored solutions based on the conditions. For example, if you're modeling climate change, it can adjust its approach depending on whether you're looking at a high-emissions scenario or a low-emissions one. The hypernetwork takes in extra information, like a climate scenario or a time frame, and uses it to generate a transport map. This map acts like a bridge, transforming a simple starting distribution, like random numbers, into a realistic prediction. It's like teaching a robot to draw a detailed portrait from a rough sketch. Only here, the sketch is basic data, and the portrait is a complex, accurate model of future outcomes. But what if the data itself is messy? Let's shift gears. Ever wonder how scientists turn abstract scenarios, like population growth or environmental policies, into predictive models? Enter shared socioeconomic pathways, or SSPs. Think of them as different plot twists. They're storylines that combine factors like technology, demographics, and policy to create possible futures. But how do you teach a computer to understand these stories? The researchers used a technique called one-hot encoding. Imagine giving each SSP its own unique color code. Like a traffic light using red, yellow, and green to signal different actions, this method lets the model instantly recognize which story it's looking at. But here's the catch: time. A computer doesn't inherently know that 2050 comes after 2025. That's where positional encoding steps in. It's like teaching the model to read a story in order. If you're told the cat chased the mouse, the word sequence matters. Positional encoding gives the model clues about when things happen, so it can spot patterns over decades. The team tested their model by predicting economic trends under each SSP. The data, visualized in box plots, those charts with boxes and whiskers. Wider boxes mean more uncertainty, like a weather forecast that says maybe rain, maybe sun. For example, countries like Canada and Colombia had wide boxes, suggesting their economic futures are tricky to pin down. Meanwhile, Germany and Spain showed narrower boxes, meaning the model was more confident in its predictions. Here's the kicker: this wasn't just guesswork. The model learned from real data. When they compared its predictions to actual historical trends, it matched pretty closely, especially when it came to how sensitive outcomes were to key factors. One parameter, clogistic, stood out as a major influencer. The model caught that sensitivity, proving it's not just random luck. So what does this mean? It shows some futures are more predictable than others. For policymakers, this could mean focusing resources on regions with high uncertainty or refining scenarios where data is shaky. And for all of us, it's a reminder that while the future is uncertain, science is getting better at mapping out the possibilities, step by step, like reading a story one sentence at a time. Next time you hear about climate or economic forecasts, remember, behind the numbers are stories, and now, machines that can help us read them. Thanks for watching. Stay curious.